Yes. Hello students. Welcome to the session. Welcome to Unacademy Telugu channel. Yes students, all of you, good evening. Before starting the today concept, yes, let me introduce myself. Yes students, my name is Surendra Babu. For 10 years, I am educating the students for GATE, ESE and PSUs in electrical and electronics engineering. These are the subjects I am teaching for electrical students: power electronics, power systems, electrical machines, electrical and electronic measurements. Yes students, and this subject I am teaching for instrumentation students, that is the transducers and mechanical instrumentation. Students, apply my promo code BABU10, get the 10% discount on Unacademy Plus subscription. And also use my promo code BABU10 to unlock our Unacademy learning app. Yes, students, please concentrate. Yes, sir. These are our Unacademy subscriptions. There is a plus subscription and iconic subscription, sir. If you select the plus subscription, these are the benefits we can get, sir. If you select the plus subscription, what are the benefits we can get, sir? Live classes, crash courses, weekly tests, doubt solving sessions. That is in both English and Hindi, it is available. These are the benefits we can get if you select the plus subscriptions. Yes, students, come to the iconic subscription. Sir, if you select the iconic subscription, what are the benefits we can get, sir? There is a personal coach is available, study planner sessions, study booster sessions, personalized test analysis, preparatory study materials, sir. All these are the benefits we can get if we select iconic subscription. That means along with plus subscription, if you want this extra benefits also means, then you go for the iconic subscription, sir. Yes student, this is about our Unacademy plus subscription and iconic subscriptions. Sir, how to get our Unacademy learning app, sir? Students, you follow these steps to get our Unacademy learning app or to install our Unacademy learning app. Sir, search Unacademy learning app in your Play Store. That is the first step. In the second step, you install the app, sir. You install the app. Yes, sir. The third step is select your goals, sir. Manage your goals. Now you are in GATE and ESE. Then select the GATE and ESE, sir. Then select plus. Then get the subscription, sir. Okay, these are the steps you follow. You get our Unacademy learning app, sir. Yes, sir. After installing and after getting the subscription, to unlock our Unacademy learning app, use my promo code BABU10, sir. Yes, sir. Sir, what are the course fee details for plus subscription and iconic subscription, sir? What are the benefits are there in plus subscription? If you want all those benefits means, then these are the course fee details for plus subscription, sir. This is for 12 months. This is more popular. 12 months program is more popular. This is for 1 year, sir. For plus subscription, apply my promo code BABU10. Get the 10% discount. After 10% discount, you pay only 27,225 rupees. Sir, what about for 18 months program? This is for 1.5 year program, sir. For plus subscription. Apply my promo code BABU10. Get the 10% discount and you pay only 34,650 rupees, sir. This is also for plus subscription for both GATE and ESE, sir. This is for GATE and ESE. Not for one course. These are two courses, sir. For both GATE and ESE. And these are the course fee details, sir. It is a 24 months program. That is a 2-year program, sir. Then apply my promo code BABU10. Get the 10% discount. After 10% discount, you pay only 39,600 rupees, sir. Okay, these are the course fee details for plus subscription. Yes, students, please concentrate. Sir, this is the course fee details for iconic subscription, sir. For iconic subscription for a 12 months program, that is a 1-year program, apply my promo code BABU10, get the 10% discount and you pay only 45,225 rupees. Okay, this is also for iconic subscription. This is for 2-year program, sir. That is a 24 months. That is a 2-year program. Apply my promo code BABU10, get the 10% discount and you pay only 66,600 rupees, sir. Okay, these are the course fee details for plus subscription and iconic subscription. Yes, sir. These are the plus batches taken by the top educator for electrical and some ECE, sir. There is so many batches are running in plus batches. You please concentrate for target ESE prelims 2021. That is for electrical. Rank booster batch for gate 2021. This is for ECE. Target ESE prelims 2021 for electrical batch. Rank booster batch for gate 2021. This is for electrical batch, sir. You please concentrate, sir. These are the batches are running in who are taking the plus subscription, sir. And these are our top educators who are teaching in plus subscription for both electrical and ECE, sir. You please concentrate. Yes, students, you please concentrate. This is our Unacademy GATE Telugu December month schedule. These are the subjects are going in December month schedule. Along with the timings also it is given. You please concentrate, sir. And these are the subject in the crash course, sir. Power electronics, EDC and aptitude. Along with the timings also it is mentioned. You please concentrate. This is a communication system 4 p.m. to 5:30 p.m. Electrical mission 4 p.m. to 5:30. Engineering mathematics 5:45 to 6:45. Power system 7 p.m. to 8 p.m. sir. Aptitude 8 p.m. to 9 p.m. sir. You please concentrate. Along with the timings also it is mentioned. Please follow all these timings to get the more knowledge on each subject, sir. Yes, students, this is our Unacademy combat. This next combat is goes live on December 29th 6 p.m. sir. After successful of first combat, now we have the second combat, Unacademy combat program, sir. December 29th 6 p.m. sir. Please register all of you. Then you can participate this Unacademy combat, win exciting prizes, sir. You can win exciting prizes. There is rank 1 to 3 is also there, rank 4 to 50. That means up to rank 50. Then there is exciting prizes are there, sir. You please participate in our Unacademy combat, sir. You register free. This is enroll for free, sir. It's a free registration, sir. The program will be December 29, 6 p.m. sir. Yeah, this is eval for gate 2022. This electrical batch A started already on 21st December, sir. This is both in English and Hindi. And you join this course, use the code EGATE10, sir. This also for eval for gate 2022, sir. It's a gate 2022. It's a ECE batch already started on 21st December, sir. Then use the code to join this course. Use the code ECE GATE10, sir. Sir, this is pre-special class series. Know your basics for gate 2022 and 2023, sir. A complete roadmap to approach each subject of every branch, sir. For every branch, this is a free special class series, sir. It's a mechanical engineering, civil engineering, electrical engineering, ECE, CS and IT and chemical engineering, sir. For every branch, if you want to know the basics, then this is for gate 22 and 2023, sir. For free special class series, sir. It is a free special class series. Students, it is already started in December 20. All of you please follow this program. That's a free special class series, sir. Yes, students. Now see the today concept. Yes. Yes, students, all of you, good evening. Yes, sir, all of you, good evening. All of you, good evening, sir. Today concept is in fault analysis itself. I am going to discuss three-phase short circuit analysis on alternators. Three-phase. In the last session, in the yesterday session, I discussed about. In the last session, I discussed about what is the three-phase short circuit analysis on transmission lines. Today I am going to discuss what is the three-phase short circuit analysis of alternator under no load conditions. Three-phase short circuit analysis of alternator under no load conditions. Yes, students, please concentrate. It's very important topic who are preparing for GATE, ESE and PSU, sir. What are the formulas I will give? Those formulas are very important to solve the problems also. Yes, students, you please concentrate. Yes, first let us consider an alternator without any fault, sir. Before fault, first you will see the what is the alternator. Yes, sir. This is the before fault condition, sir. This is the before fault condition. Let this is the IB, sir. Okay. Let this is the R phase, and this is Y phase, and this is the B phase. This is no load, sir. That's why all the currents are zero. No doubt at all. IR, IY, and IB is zero, sir. This R phase, Y phase, and B phase. Yes, sir. We know the operation of the alternator. We know the operation of the alternator, sir. Whenever field is excited, now I am assuming that this rotor is the field, sir. Rotating field type. This is the rotating field type. There is a two constructions are there. Rotating armature type, rotating field type is also there. Here I am taking the rotating field type, sir. If this rotor is rotated, this rotor flux is also rotating with ns speed, sir. This rotor flux is cut by this armature conductors. There is induced EMF. That induced EMF is taken as an excitation EMF. All these concepts you know, sir. What the operation of the alternator? All these. That means, sir, if the alternator is under before fault condition, here I am assuming that no load condition. No load condition means what the armature currents are? Armature current is 0. Yes, sir. If you draw the equivalent circuit of alternator, under before fault condition, sir. All of you well known this one. Before fault condition. Later, I am neglecting armature resistance, sir. By neglecting armature resistance. I am drawing this one by neglecting armature resistance. I am drawing this equivalent, sir. Yes, students, all of you know this one. By neglecting armature resistance, mainly this alternator is having the three drops, sir. One is armature resistance drop, armature reactance drop, and leakage reactance drop, sir. It is having the three drops. Then by neglecting armature resistance, here I am neglecting the RA, sir. Actually, what the total synchronous impedance of? The alternator, sir? We know this one, RA plus J into XA plus XL, sir. This concept you know, XA plus XL, sir. This is equal to RA plus J into XA plus XL is nothing but a XS, sir. It is equal to, this is the synchronous impedance, sir. What this XS are? This XS are is also called direct access reactance. Generally it is taken as a direct access reactance. But this is due to armature reaction effects, sir. Yes, all this, what is the armature reaction effect, all this that you know in electrical mission subjects, sir. But mainly concentrate this minimum knowledge. What the synchronous reactance equal to armature reactance plus leakage reactance. Now I am representing this one. I am drawing the equivalent circuit, sir. I am drawing the equivalent circuit of alternator by neglecting the armature resistance. Let this is the XL, sir. This XL is the leakage reactance and XA is the armature reactance. That means before fault condition, it consists of how many reactances, sir? 2 reactances. It consists of 2 reactances, sir. Students, please concentrate. It consists of 2 reactances. One is armature reactance and leakage reactance. Let this is the excitation voltage. This excitation voltage is at angle of delta, sir. I am taking easy at angle of delta. Okay. This delta is, what is the delta that you know, sir? This is the load angle, or if you taken as it is a power angle. Okay. That is angle behind the synchronous impedance. This is the GZ is the generated voltage excitation EMF. Okay. Now this is the generated voltage. This XL equal to leakage reactance. Now what is this total, sir? This total XS or it is also equal to XD, sir. Synchronous reactance or direct access reactance that equal to XA plus XL, sir. Here I am not assuming that any load, that's why no load current. What the armature current, sir? Under no load condition, the armature current equal to 0, sir. Under no load condition. Here I am not connecting any load. There is no any closed path here. Understood? Armature current equal to 0. Then one more point you remember, sir. In the case of alternator, the generated EMF, in the case of alternator, the generated EMF, whatever the EZ is there, lacks the main field flux. By angle of how much, sir? 90 degrees. This is the excitation EMF or generated EMF, sir. The excitation EMF or generated EMF lacks the main field flux. The main field flux is denoted by pi m or pi f, sir. You can denote either pi m or pi f. It is denoted by this field flux. Main field flux is denoted by pi m or pi f. This lacks the flux by angle of 90 degrees. This concept also you know, sir. That means these are the observation before fault. If you consider the synchronous generator or alternator before fault condition, there is excitation EMF is there. then that excitation EMF, and there is a two drops are there. One is a leakage reactance drop, armature reactance drop, and also there is armature resistance drop is also there, sir. But this armature resistance drop I am neglecting. That's why I am taking only two reactances, sir. Leakage reactance and armature reactances. This is the if the generator is before the fault condition. Now the concept I want to explain, sir. If the three-phase short circuit fault is occur on the alternator, if the three-phase short circuit fault is occur on the alternator, then what is the observations in the three-phase alternator? Yeah, that I want to discuss, sir. Yes, students, please concentrate. Yes, sir. Let assume that alternator under short circuit fault. Let assume that there is a three-phase short circuit fault is occur on the alternator. There is a three-phase short circuit fault. When the three-phase short circuit fault is occur means because of closed path, now which current is exist? Now there is a flow of armature current. This current is nothing but which currents are flow fault current. Now this current is treated as a which currents are fault current. Understood? That let assume that a three-phase short circuit fault is occur on the alternator. If the three-phase short circuit fault is occur, sir, already in the previous session I already discussed it, sir. If the fault is occur on the alternator, if any three-phase fault is occur, there existed two components, sir. Then the total current is having the two components. One is transient current, another one is steady state current, sir. Now it consists of two components. One is transient current and steady state. This is the AC component. Steady state component is the AC component, sir. In the previous session already I given, sir. No need of derivations all this again. This transient current is which one, sir? This is a DC current, sir. It is a DC absent. It is a decaying current and DC current, sir. It is a DC current, sir. That means whenever a three-phase fault takes place, then it consists of two components. One is transient component, another one is steady state component. IT transfer, which one, sir? Transient component. As students, please concentrate. It is a transient component. Then this is the which one, sir? Steady state component. It is the steady state components. Yeah, this is the steady state component. Actually, it is a AC component. It is a sinusoidal component. That means it consists of two components, transient and steady state component. Sir, this I given. The nature of the fault current is mostly inductive, reactive in nature, sir. We are assuming that completely the resistance is negligible. That's why whatever the fault current is there, that fault current is flowing through inductive nature only. We are assuming that is the inductive nature, sir. The flux produced by AC component is, then whatever the flux produced by the AC component is rotating at synchronous speed, and there is no speed of the rotation of DC offset, sir. Yes, sir. Here now there exists a current, sir. Before the fault, we are assuming that alternator is under no load condition. That's why there is no current, sir. If any fault takes place, now the current is flowing through the windings. Now the current is flowing through the armature windings, sir. That means there exists armature current. This armature current is a which current, sir? Here it is a fault current, sir. This armature current is a which current, sir? Fault current. Now, if this fault current is passing through the three-phase windings, there is a rotating magnetic field is produced. That means there is a flux is produced. Sir. That flux is actually because of steady state component is the AC component. Then whatever the flux produced by steady state component, this flux is rotated at a speed of ns, sir. Because it is a AC current, that's why that flux is rotated by a speed of ns, sir. But what about the flux produced by the transient component? It is a DC current, it is a constant current, sir. Then whatever the flux produced by the transient component, it does not have any speed, sir, because it is a constant flux, sir. It does not have any speed, sir, because it is a constant flux. Because DC current, constant flux. AC current, then alternating flux. The speed of this alternating flux is ns speed. It is rotated at a speed of ns, sir. This I am telling that. That means the nature of the fault current is mostly inductive, reactive in nature. Why? Because we are assuming that mostly inductive, the resistance is negligible. The flux produced by AC component is rotating at a speed of ns, sir. But the flux produced by DC component is not rotating because it's a constant current, it's a constant flux. Yes, sir, please concentrate. Now see, the flux produced by the AC component, does influence the rotor flux so that rotor air gap flux may become demagnetized. The magnetizing coupling may fail, sir. Yes, sir. It's a very important observation, sir. whatever the flux produced, that means now the flux produced by this AC component, then which flux are that one? Armature flux. That is the flux produced by which components are? Steady state component. We know that, sir. Before fault condition, we know this one. This is the generated EMF, sir. This is the generated EMF. This is the main field flux R. This is the main field flux R is represented by pi m r pi f, sir. Main field flux. This is represented by pi m r pi f, sir. Now there is another current. Which current is flowing, sir? Fault current is flowing. Because of this fault current, there is armature flux is produced. That armature flux is a steady state component, that is pi as is produced. Because steady state component, there is a armature flux is produced, sir. Now this armature flux lacks the generated voltage by angle of 90 degrees, sir. Yes, students, this armature flux lacks the generated EMF by angle of 90 degrees, sir. Why it is lacking the by angle of 90 degrees, sir? We are assuming that it is a purely inductive nature. Then it is lacks by angle of 90 degrees means, sir, it's a 90 degree lagging, sir. 90 degrees lagging means what the effect of armature reaction, sir? What the effect of armature reaction? This is the main field flux, sir. This is the main field flux. And this is the, yes, sir, this is the main field flux. The main field flux and armature flux is opposite, sir. It's what the phase difference are 180 degrees, sir. Then this is, if you assume that this is the main field flux, sir, and this is the armature flux, these two are opposite. If these two are opposite, it means, sir, what the effect of armature reaction, sir? The effect of armature reaction is complete is a demagnetizing effect. Understood, sir? Now, because of this demagnetizing effect, if you assume that this is the main field flux, this is the armature flux due to steady state component. These two are opposing because of 180 degree phase difference. These two. That means now armature flux is opposing the main field flux. Armature flux is opposing the main field flux means what the effect of armature reaction? The effect of armature reaction is demagnetizing. Once it is a demagnetizing effect means due to fault, whatever the flux is produced, that flux reduces the main field flux. Continuously the main field flux is reduced, then there is a problem with the coupling may be failed. The coupling between the stator and rotor may fail, sir. That is the problem. Now what happened here? Now actually if it is happen continuously, the main field flux will reduce us. If the main field flux is reduced us, what happens, sir? There is a coupling may be fail. That is the coupling between the stator and rotor will fail. But to maintain the coupling between the main field flux and stator flux, now what happening here? In order to maintain the coupling, what happening, sir? This concept important, sir. Now see, in order to maintain the magnetic coupling, the rotor air gap flux to be maintained as constant by strengthening the rotor flux or oppose the armature reaction produced by AC component with the help of counter-induced EMF in the rotor field winding and also in the damper winding of rotor due to the flux produced by the DC offset of, that is the this is offset current of the faults. That means it's very important concept, sir. Now, in order to maintain the magnetic coupling, here we want to maintain the magnetic coupling, sir. How that magnetic coupling is maintained? Yes, sir. That means, let us consider one concept here, sir. Let us consider, it's a simple. Okay, this is the stator and this is the rotor, sir. Okay, this is the rotor. Here I am drawing this one. How the coupling is maintained? By strengthening the flux. Sir, what happening here, sir? Because of this fault takes place, there is a armature flux is produced. Because of that armature flux, what happening? Demagnetizing effect takes place. Because of that demagnetizing effect, main field flux is reducing. If the continuously main field flux is reducing, then what happens, sir? There is a coupling will fail. Okay, then magnetic coupling will fail. Then for that, what happening here? We know that in a synchronous mission, we are using the damper bars also. Let this is the rotor field winding. It's a rotor field winding, sir. The rotor is excited with the DC. The field is excited with the DC. Let this is the rotor is rotating this direction. Now, what I am telling that if there is a fault takes place, Here which flux is produced, sir? There is a two fluxes are produced. Two fluxes are produced. One is a transient flux. The another flux is which one, sir? One is transient flux. The another flux is which one, sir? That is the steady state flux. That is steady state component flux. Steady state component flux is produced, sir. Here there is a pi s is also produced. But this pi s is rotating at what speed, sir? It is rotating at what speed? Ns speed, sir. Ns speed. Yes, listen, sir. Now this pi s, whatever the stator flux, that is whatever the flux produced due to steady state component, that is rotating with ns speed. This flux links with field windings. This flux is links with the field windings, sir. Once this flux is links with field windings, there is a emf is produced. There is a emf is produced. That emf will circulate the current. That emf will circulate the current. Because of that, we are getting the flux also. We are getting the another flux, sir. That flux is treated as a whatever. That means, if this is flux, there is an induced EMF. That induced EMF will circulate the current. Then because of that induced EMF, there is a circulating current. Because of that circulating current, the flux is produced, sir. That flux always opposes the steady state component flux. That flux opposes according to Lenz's law. Whatever the flux is produced due to steady state, there is a flux is produced pi fs. This pi fs flux opposes the pi s. Opposes the pi s means indirectly strengthening the which flux, are strengthening the which flux, are rotor flux. It strengthens the rotor flux. Opposes this flux means strengthens this flux. Similarly, yes, sir, even though it is a constant flux, but our rotor is rotating at what speed, sir? Ns speed. Here rotor is rotating at ns speed. Rotor is rotating at ns speed, sir. If the rotor is rotating at ns speed with respect to this phi t, rotor is rotating at ns speed. This phi t flux links with the damper bars, sir. It links with the damper bars, sir. Then it also produces the flux, sir. It also produces the flux. Whenever this pi t links with the damper bars, this is a conductor, sir. It is a rotating conductor. Rotating conductor cuts the constant flux. Yes, sir. This rotating conductor cuts the magnetic flux. There is induced EMF. This induced EMF circulates the eddy currents. That eddy currents will produce the flux. This is the flux produced due to which one, sir? DC offset flux. That DC offset flux is produced in which windings, sir? Damper windings. There is a pi dW is produced. It's a pi dW is produced. That means, according to Lenz's law, who is the response, sir? Pi t is the response. Who is the cause, sir? Pi dW is the cause, sir. That means pi t is produces the flux of pi dW. This pi t, how this pi t will produce us, sir? This pi t will induce us the EMF in damper bars. This EW will circulate the circulates the current, sir. Circulates the current, IDW. This IDW produces the pi dW again, sir. This IDW will produce the pi dW. But this pi dW opposes pi t, sir. Opposes pi t, sir. It is opposes pi t means indirectly strengthening the main field flux, sir. Strengthening the main field flux. It is strengthening. This is strengthening the main field flux, sir. Yes, students, please concentrate. It's strengthening the main field flux, sir. It's strengthening the main field flux, sir. That means it's strengthening the main. Similarly, what about this pi s, sir? This pi s produces the induced EMF in EF. Produces induced EMF in EF field winding. That field winding will circulate the current. Because of that, there is a pi fs is produced, sir. Pi fs is produced. This pi fs opposing the pi s, sir. According to Lenz's law, opposing the pi s. Opposing the pi s means indirectly this pi fs, that is the flux due to steady state component. This is the flux due to transient component, sir. This is the damper winding flux. This pi fs opposes, that means strengthens the main field flux. It strengthens the main field flux, sir. It strengthens the main field flux. That main field flux is strengthened. That means, like this, we are maintaining the main field flux is strengthened. Then once the main field flux is strengthened means, then what about the induced EM? What are the main flux we are maintaining as a constant, sir? That means Actually, this is the main flux, sir. Let us assume that pi m is the main flux. Now, what is the resultant flux are pi s? The resultant flux is pi s. The resultant flux is pi m minus pi s. If fault is takes place, pi m minus pi s plus pi t, sir. Pi s plus pi t. Now, because of pi s, there is another flux is produced. Here, which is produced, sir? Pi f s is produced in the field winding. Because of pi t, there is another flux is produced. Pi d w is produced, sir. These two fluxes will strengthen the main field flux. These two are reducing, but this is strengthening. Then we are maintaining the main field flux is constant. We are maintaining the main field flux is constant. These two is reducing, sir. But again, these two are increasing. Understood? These two are reducing this flux. Pi s and pi t reducing this flux, sir. But because of these two fluxes, because of induced EMFs in the field windings and whatever this damper bars, these two again two fluxes are created. These two fluxes will aiding the pi m means strengthening the main field flux. But these two fluxes are reducing the main field flux. Then this pi m remains constant. That means here the concepts are, in order to maintain the magnetic coupling, the rotor air gap flux to be maintained as constant. Which ones are? Pi m you want to maintain constant, sir. By strengthening the rotor flux or by opposing the armature reaction produced by the AC component with the help of counter-induced EMF in the rotor field windings and also damper windings. How these two fluxes are produced, sir? These two fluxes are produced because of the induced EMF in the main field winding, because of the induced EMF in the damper windings, because of induced EMF in the damper windings. Now the question is, now like that we are maintaining the flux is constant, sir. Now the question is, how much time this pi dw will present? How much time this pi fs will present? That depends on the transient period, sir. There is a subtransient period, there is a transient period, and there is a steady state period. Yes, sir. That means there is a two fluxes. There is a extra two fluxes are created. These, in order to represent the physical representation of these two fluxes, in order to represent these two fluxes, this pi fs flux is represented by physically by using the field reactance, XF. That is a field reactance. Physically, how you can represent these two fluxes? By using imaginary reactance. That reactance I am taken as XF. XF is the field reactance. This pi dw physically represented as by using the reactive components. Sir, we never represent using resistive component. We always represent the flux physically by using the reactance component only. Sir, why, sir? Flux does not cause us any losses, sir. Flux causes only drop. Once the flux causes only drop means, sir, we always represent only with reactance. It is not represented with resistance, sir. Students, please concentrate. Now, physically this pi dw is represented by, xdw. If you want to represent physical means we can use some reactance. This is the reactance due to damper winding flux. This is the reactance due to field flux. That field flux is produced by the steady state component. Understood, sir? This is XF. This is XdW. Now, how much time this XdW will present? How much time this XF will present? That depends on transient conditions, sir. Now, I will see, sir. What do you mean by subtransient period, sir? You please concentrate. What do you mean by subtransient period? This subtransient period is nothing but from the instant of fault to please note down, sir, this from instant of fault to the instant when pi wd, that is damper winding flux, becomes to 0. Pi dw, that is pi dw. I am taking as a pi dw. That is a damper winding flux is 0. From the instant that is pi dw equal to 0. Okay, from the instant of fault to the instant when pi dw equal to 0 becomes 0 is taken as a subtransient period. But you know this one, sir. The subtransient period is measured as for 1 to 2 cycles. This is for 1 to 2 cycles. This is for 1 to 2 cycles. Subtransition period is measured as well. That means during subtransition period, there existed 3 fluxes. During subtransition period, there existed 3 fluxes. That is main field flux is present. At the same time, which flux is present, sir? That is pi dw is present. Pi of t is also present. Pi dw is present. Pi of t is also present. That's why during subtransition period, the equivalent, the electrical network of the generator is represented as. Therefore, during subtransition period, yes sir, the electrical network of the generator is represented as the electrical network of generator. This electrical network of generator is represented as sir, how we can represent, sir? Represented as, it consists of, we know already, this is the generator or alternator. Let this generated voltage is easy, sir. This is easy, and it consists of leakage reactance, and there is already which reactance, sir? Under normal condition, before fault, there is armature reaction. But along with armature reactance, there is additionally which reactances are? Two more reactances. Which one, sir? This is the field reactance, and another one is damper winding reactance. It consists of damper winding reactance. During this period, sir, this period is nothing but from the instant of fault to pi dw0. That means during this period, pi dw is also present. When this period will complete, sir, when pi dw becomes 0, then only this period is completed, then it enter into transition period. That is the meaning. During this period, at the instant of fault to the pi dw equal to 0, this total period is nothing but a subtransition period, sir. Understood? That means during this period, pi dw is present. That pi dw is practically, it's represented as the physical significance is given by xdw. This is a damper winding reactance. This field winding reactance, XA is the armature winding reactance. This XDW is the damper winding reactance. Yes, sir, I am representing like this. Okay, this is easy. Generated voltage is easy. In this case, what is the total reactance offered by the alternators? Under subtransition period, what is the total reactance offered by the alternator? This total reactance, it is taken as a direct access reactance, sir. Then XL plus. These three reactances are parallel, sir. XA in parallel with XF in parallel with XDW, where XDW is the damper winding reactance. Okay, this is the subtransition reactance. The subtransition reactance is denoted by XD double dash. The subtransition reactance is denoted by the XD double dash. Yeah, this is the resultant reactance. This XD double dash equal to XL plus XA in parallel with XF, that is in parallel with XDW. All these three reactances are in parallel. Yes, students, please concentrate. Okay, that is we are representing with XA, XF. What is XDW, sir? Here, it is the opposition of armature reactance due to which one, sir? That pi t. Due to pi t. That means XDW is the damper winding reactance. Damper winding reactance. This is represented the opposition of, it represent opposition of or aiding of main field flux or opposition of armature reaction. This is opposition of armature reaction due to Due to which one it is created, sir? Pi t. Due to pi t. What is XF, sir? What is XF here, sir? It's represent, where XF represent. XF represent opposition of armature reaction. Opposition of armature reaction. Armature reaction. Due to which one, sir? It is created due to which one, sir? Pi s. This is steady state components. It is armature. This is due to pi t. This is the pi t, sir. It represents opposition of armature reaction due to which ones are this one? This is due to pi t. This is pi s. This is actually it is represented for pi f, sir. It is represented for pi f t. Here I already given this one. Okay, this is for pi fs and this is for pi dw. This is pi fs and this is for pi dw. Okay, sir. This is for pi dw. Damper winding. That damper winding flux is this pi dw is opposes the armature reaction flux. Pi fs is also opposes the armature reaction flux. This is the resultant reactance, sir. XD double dash. This is the subtransient reactance. It is a subtransient reactance. XL plus XA double dash plus XF in parallel with XD double. All these are in parallel. This is a subtransient. Therefore, subtransient, that is D-axis subtransient reactance. I am adding on page here. That is the D-axis direct axis, direct axis subtransient reactance equal to subtransient reactance equal to what you write, sir? Subtransient reactance XD double dash is equal to this XA plus what this one, sir? It's also there XL, not XA. This is XL plus what this one, sir? XA in parallel with XF in parallel with XDW. XDW. Okay, this is the total reactance. But here, under this condition, what is under subtransient period? What is the current in the alternator? What is the current in the alternator? Then we can define as initial symmetrical RMS fault current. Initial symmetrical RMS fault current, sir. RMS fault current. I am not calculating offset current. This I am calculating symmetrical. Initial symmetrical RMS currents. RMS current. This is denoted by IF double dash. IF double dash. Initial symmetrical RMS current. That is I symmetrical. I symmetrical is IF double dash. This IF double dash equal to what you write, sir? What the generated EMFs are? EG by XD double dash. Yeah, this important formulas. These formulas are important to solve the problems who are preparing for gate point of view. IF double dash is initial symmetrical RMS current. It is the initial symmetrical RMS fault current or subtransient RMS fault current. Initial symmetrical RMS fault currents. It is also called, where IF double dash is also called subtransient RMS fault current. Subtransient RMS fault current. It's a RMS fault currents. RMS fault current. Students, please concentrate. It's a, how to calculate this one? Whose reactance? What is XD double dash? This one. XD double dash is this XD double dash. That is IF double dash is EG by XD double dash. Yes, sir. Sir, this is XA in parallel with XF in parallel with XD double. What is the observation here, sir? If these are not present, only XL plus XA. Only XL plus XA. But these two reactances comes in parallel with XA. In parallel combination, the reactance is reduces. In parallel combination, this resultant reactance will reduce. When the resultant this is reduces means this is reduces means what the XD double dash is also, sir, less. That means under subtransient condition, what is the reactance offered for the flow of current is less, sir. Once it is less means, sir, this subtransient fault current is very high. Among all the fault currents, the subtransient fault current is high because of XA, because of XF and XDW is in parallel with XA. this term, this reactance term is reduces. Then total reactance XD double dash will reduce. When the XD double dash is reduces means what is IF double dash? This IF double dash is more. That's why under subtraction condition, whatever the fault current is there, that fault current is high. And under subtraction condition, we can get the more fault currents. Here I am talking about only for symmetrical. I am not talking about DC offset current. I am not calculating DC offset current here. But that calculation already used in even the transmission line also. It is a constant current. But mainly here I am calculating which one, sir? I am calculating the symmetrical current under, that is a steady state component of current. Initial symmetrical RMS fault current is also called subtraction current, whose value is high. Why? Because this XD double dash is less. XD double dash is less. Yes, sir. Now see, after completing 1 to 2 cycles, sir. After completing 1 to 2 cycles, that is subtraction period. That is subtraction period is completed, sir. Subtraction period. Once the subtraction period is completed, then this pi dW goes to 0. Pi dW 0 means the current through the damper windings, is 0. Why the first this pi dW only 0? Why not pi f is 0? The reason is, we know, sir, that depends on the time constants. Among all these field winding and the damper winding, the time constant of the damper winding is less as compared to field winding time constant, sir. Why? Because we know that for damper winding, its resistance is high. When the resistance is high, if you calculate the time constant of damper winding, for damper winding the resistance is high, sir. We are using damper bars, nothing but we are using high conductivity copper bars we are placing. That is whose resistance is high, sir. If the resistance is high means whose time constant is less, sir. If the damper winding time constant is less means first which component, then which component will, that is which component will goes to 0, sir? The damper winding will current goes to 0. When the damper winding current is 0, why? Its time constant is less. But what are the field time constants, sir? If you take the field time constant, LF by RF, sir, LF by RF. But you know that field inductance is very high. That's the reason why its field time constant is also good. Then it can exist for a long time as compared to damper winding. That's why after completing 1 to 2 cycle, this pi dW goes to 0, sir. That's why from at the instant of fault to pi dW is 0 is taken as a subtraction period. That is taken as a subtraction period. Then after completing this subtraction period, pi dW equal to 0. Pi dW 0 means next in a transition period, next coming transition period. For next, after subtraction period, what you can get, sir? After 2 cycles, you can get the transition period. In a transition period, there is no significance of this damper winding reactance. Why, sir? There is no significance of damper winding reactance? Because IDW equals 0. Once IDW equals 0 means it acts as an open circuit. Once it acts as an open circuit, we are not considering any reactance. Understood, sir? This dies out. That means whatever the damper winding reactance is there, we are not considering in the case of transition period. Understood, sir? Now we'll see how to measure the transition period. Yes, students, please concentrate. From the instant of transition period is from the instant of pi dW become 0 to, from the instant of, it is measured from the instant of pi dW 0 to, that is pi dW becomes 0 to the instant pi of t also becomes 0 to the instant pi of t also becomes 0. Pi of t also becomes 0. That means pi of t is not become 0 in transition period, sir. After completing transition period, at the end of transition period, pi of t is 0. That is the meaning. Also becomes 0, sir. That means, sir, during transition period, which is 0, sir? This pi dW 0. Pi dW 0 means which is 1 0, sir? XdW equal to 0. This pi dW 0 means, sir, we are not considering this XdW, sir. We are not considering this XdW. That point to remember. Pi dW0 means there is no significance of which ones are XdW. Then what is the electrical network of the generator under transition period? Electrical network of the generator is electrical network of the generator under transition period. Yes, sir. What is this one, sir? Under transition period. The electrical network of the generator under transition period, sir. What is the electrical network? Then this is the generator. This is the generator. Then it is having the leakage reactance is XL. EZ is the generated voltage. Then it consists of armature reaction reactance. Then it consists of which ones are field reactance also. But you don't consider which ones are damper winding reactance. Already at the end of subtransition period, that, sir, you know that damper winding will provides, that means if there is a oscillations, if there is more oscillations only, damper bars will comes into the action. Understood? If the oscillations are reduced, then automatically what is the damper bar action? You don't have any damper bar action. Damper bars damps the oscillations only. The oscillations are more. Where the oscillations are more, sir? During subtransition period only. In that case only there is significance of damper bars. That's why it is a XF, sir. There is a XF and generated voltage is easy, sir. Generated voltage is easy. Yes, sir. Okay, this is the electrical equivalent for the electrical network of generator under transient condition. Now what is the reactance? XD dash. This is a transient reactance. It is not subtransient, it is a transient reactance. Then XL plus this XA in parallel with XF. XA in parallel with XF, sir. Okay, this is the, what is XD dash here, sir? Where XD dash is which one, sir? Transient reactance. The XD dash is taken as which one, sir? It's a D-axis transient reactance. Therefore, D-axis, direct axis, transient reactance. Sir, why you are defining always direct axis reactance, sir? All these components, XF and XTW is opposing the armature reaction effect to make the flux is constant, to make the main field flux. But armature reaction takes place along which axis? D-axis. That's why you are defining the D-axis reactance only. Simply remember. One more point. Sir, why you are connecting in parallel? Okay, this all these fluxes is because of mutual coupling only. Because of mutual coupling only. That's why I am connecting in parallel. Okay, that is the answer only. Okay, these two questions. Why you are connecting in parallel? Because of the mutual coupling only. Why you are representing always direct axis? Because all these components except and XTW components are to oppose the armature reaction effect, maintaining the main field flux is constant. Sir, why it is opposing, sir? This is according to flux constant theory, sir. Flux, always there is a constant flux linkage. According to constant flux linkage theory, this is happening. Okay, how it is opposing, that concept I already given. Then D-axis reactance, D-axis transient reactance, D-axis transient reactance. What is the D-axis transient reactance? XD dash equal to this one, XL plus this XA in parallel with XF. Once you know the D-axis transient reactance, sir, now I want to calculate transient RMS current. I want to define transient RMS current. Then how to write transient RMS current, sir? Under this condition, what is the current? Transient RMS current. You write this one, sir. The transient RMS current, this is denoted by IF dash. RMS fault current. Transient RMS fault current. IF dash equal to, what is the voltage are? EG. What are the reactants are? XD dash. EG is XD dash. So this XD dash as compared to XD double dash, it's somewhat, it's a low, that is low value, sir. It is a high value. XD dash, you know this one, because there is no another component, there is no another parallel component. XD double dash is not there. That's why its value is increases as compared to XD. Okay, let that I will give that relation. But XD dash is more than as compared to XD double dash. Because XD double is not present, one parallel reactance is removed, then this value will increase. Understood? The transient RMS fault current equal to EZ by XD dash. Transient RMS fault current equal to EZ by XD dash. Okay, this is about transient periods. Transition period. Now, once the transition period is completed, at the end of transition period, this phi of t is also 0. Once the pi of t is also 0 means now under the steady state condition, after this transition period means how many cycles are this transition period is taken as a greater than 2 cycles, up to 5 cycles it is taken as a transition period. Then after this which comes into the action sir, steady state period. That means that once the I of t is also 0, that means in transition period that pi of t is also 0 sir. That means after completed at the end of transition period, at the end of transition period, what about this pi of t sir? This pi of t, this sir, at the end of transition period, this is pi dw0 to pi of s sir. This is pi of s taken as a that flux due to steady state component pi of s. That at the end of transition period pi of s equals 0. Pi of s equal to 0 means there is no significance of which ones are xl. To represent this pi of s only we are using this xl. But this is 0 means there is no significance of this one xf. That means in the case of steady state period, then in the steady state period the xf is also 0. Once the xf is also 0 means, when the xf is also 0 means, then what is the electrical equivalent you can represent? The electrical equivalent is represented as, this is xl. This is completely the fault is removed, sir. This is xl and this is what is this one, sir? This is xl. This is xa. Then what is this one, sir? Generated voltage. Generated voltage is. The generated voltage is easy. Now what is the equivalent reactance? This is the xd equal to xa plus xl. xa plus xl. There is no any parallel reactance here, sir. xa plus xl. Then this is taken as a, this is which ones are d-axis steady state reactance. Is a d-axis steady state reactance. Steady state reactance. What the d-axis steady state reactance are? xd equal to xa plus xl. Armature reaction reactance plus leakage reactance. Then we can define steady state or sustained RMS fault current. Steady state. A steady state or sustained RMS fault current. RMS fault currents. How we can take steady state or sustained RMS fault current? I am taken as a, this is given as a IF. Is IF equal to EG by XD. EG by XD. Sir, you have one doubt, sir. Sir, at starting before fault condition, you written the EG at angle of delta, sir. But why you are not taken at angle of delta, sir? Sir, you remember this point during short circuit fault, during three-phase short circuit fault, what is electrical power, sir? P equal to 0. P equal to P max into sin deltas. P max into sin delta. Because three-phase short circuit fault, voltage 0, then power equal to 0. P max. It's a 0 means what the deltas are? 0. That's why I'm taken as a easy at angle of 0. That's why every time I'm taking easy one. This is the reason. That means during three-phase short circuit fault condition, at before fault I represented easy at angle of delta. But here I'm not considering the deltas. That's why directly I'm written this easy by x. Now tell me, sir, if we compare these three reactances, you tell me, sir. Because initially there is a more parallel combination, the reactance is less. That's why xd double dash is less than xd dash is less than xd. That means subtransient reactance because of more parallel reactance. Parallel reactance means the resultant value is reduces. That's why xd double dash is less than xd dash is less than xd. That means which reactance is more, sir? The steady state reactance is more as compared to subtransient reactance. If reactance is less means what the fault currents are. That's why that is subtransient fault current is greater than, that is the transient fault current is greater than, this is the steady state fault current. Okay, steady state or sustained RMS fault current IF equal to EZ by XV, sir. Clear, sir? Like this is the relation. That means initially the fault current is more. Initially, then once it comes to the steady state, slowly the current is reduced. The fault current is reduced. Why, sir? It offers the high reactance. Steady state reactance is more as compared to transient and which ones are subtransient reactance. The subtransient reactances are less because of XDW and XF is in parallel. Transient current is somewhat more as compared to this one, sir. Why? XDW is removed. But XD is high, sir, because XF is not there. XDW is also. That parallel reactances are not there. That's why this resultant reactance is more. Clear, sir? Okay, this is about what exactly IF double dash, IF dash, and IF. Here, two more currents also I want to give, sir. Already I explained in the case of a transmission line. Here also I want to give maximum momentary current, sir. Maximum momentary current. How you can write this one, sir? I am writing two more formulas here. One is maximum momentary current. This I already calculated in the transmission lines also. Maximum momentary current. Yes, students, please concentrate. The maximum momentary current. This is IM, sir. IMM is given. This is how to calculate, sir. 2 root 2 IF double dash. What is IF double dash, sir? This is I symmetrical current. This already given. Then momentary current, RMS momentary currents. RMS momentary current. RMS momentary current. This also I calculated in the previous session, sir. RMS momentary current. These two currents also I am giving. This is RMS momentary current. IM RMS. This IM RMS. How you calculate, sir? This I given 1.6 times of IF double dash. Where IF double dash is also equal to symmetrical currents. It is also equal to symmetrical current. 1.6 times of IF double dash. Actually, it is a root 3 times of IF double dash we are getting, sir. But practically, theoretically 1.73 times. But practically you can take this is because theoretically we are taking some assumptions. If you neglect all those assumptions, then you take 1.6 times of IF. This is the maximum momentary current. The maximum momentary current is 2 root 2 times of IF double dash RMS. These two currents are important in circuit breaker designs. In circuit breaker selection, this maximum momentary current and RMS momentary current is understood. 2 root 2 IF double dash, this 1.6 times of IF. Clear, sir? You please come. What is IF double dash here? Subtransient current. Okay, this is the observation during transient condition. If any three-phase short circuit fault takes place on an alternator, what are the observation during the subtransient period, during the transient period, and during steady state period? During steady state period. Why these currents are? Why these reactances are like this? Because of damper winding reactance and field winding reactance. Why this damper winding reactance and field winding reactance comes? Because of maintaining the flux is constant. Under short circuit condition, you want to maintain the flux is constant. Otherwise, continuously demagnetizing effect takes place. We can't maintain the rated voltage at the alternator terminals. Understood, sir? Because of demagnetizing effect. Okay. Now, see the observation. Okay, these are the waveforms for short circuit current waveforms on no load operating alternators, sir. You see in this one, during transient period, sir. This is subtransient period. During subtransient period. During subtransient period, 1 to 2 cycles, sir. During subtransient period, the current is very high. Current is very high. I am not considering DC effect. Without considering the DC effect, here I am taking this one. Without any offset effect, I am not consider. With offset effect, how that waveform that you see even in the transmission lines also. But here see, I am not considering. Why? Because the DC effect will changes from one phase to another phase. I told already. Phase to phase, the DC effect is changes. Okay, but later on I will give that waveform. If DC effect is considered on each phase, how the waveform we can. First here I am giving without any DC effects. Now see, this subtransient envelope, sir, we are getting more current at during subtransient condition. This is the transient envelope, sir. This is the transient condition. Slowly the current is reduced. Then in steady state, the current is less. That means in this period we are getting IF double dash. In this period we are getting IF dash. In this period we are getting IF dash. You please concentrate, sir. This is IF dash. But here we are getting IF. That's why which is greater, sir? IF double dash is greater than IF dash is greater than IF, sir. That's why this IF during this period, what the reactants offered, sir? This is XT double dash. During this period, what the reactants offered? XT dash. During this period, what the reactants offered? XT, sir. Understood? This is the three-phase short circuit. See, during subtraction period, sir, during this period, we are getting more current. Then slowly the current is reducing. The fault current is reducing. In transition period, this is the magnitude of current you can get. Once you can go to the steady state envelope, this is the steady state current. The steady state current is reduced to steady state fault current is less as compared to this. Understood, sir? Okay, this is about three-phase short circuit current waveform of no load operating alternator. See this one. In the case of transmission lines, in the case of alternators, see the comparisons. Where we are not getting like this decreasing amplitude like that. We are not getting decreasing amplitude like this. Where unsymmetrical waveform here. But here also there is unsymmetrical because of DC effect. But I am not considering. Here I am drawing only by considering the symmetrical current by neglecting the DC effects. DC offset effect. Now the same waveform if you draw in terms of logarithmic scale, sir. This is you drawn in the case of logarithmic scale. Logarithmic scale. By taking the logarithmic scale, then we can get the waveform like this. That means in subtransition period, during this period, we can get the more current. In transition period, slowly the current is reduced. Then under steady state period, here this is the current we have. This is on logarithmic scale. This we can take as a this is magnitude of current in the logarithmic scale. This you take the time. On this axis, we are taking the time. Understood? This is during which period, sir? Subtransition period. That is, let us assume it's a T double dash. Subtransition period is T double dash. From this point to this point, this is which one, sir? Transition period. Let this is T dash. The transition period is T dash. Then this period is taken as a T. This period is taken as a T. Okay, this is which one you can take? This is the subtransition period. T double dash. If you take a logarithmic scale, so you can easily understand. Subtransition period, transition period, steady state periods. Okay, this is about three-phase short circuit current waveform on no load operating alternator by using the logarithmic scale. Okay, that you concentrate. And these are the three-phase short circuit current waveforms for each phase. Each phase by considering the DC offset effect also. Okay, by considering this DC offset effect, we can get some unsymmetry also, no doubt at all. But here this is the DC offset effect. But here also same, sir. Because during transition period, we can get the more current. Subtransition period, slowly the current is reduced once it comes to the steady state. Then once it comes to the steady state, the current is reduced. Here also same. This is the DC component of current. Because of DC component of current, we are getting which one, sir? It is unsymmetrical. This we are getting the unsymmetrical. Understood, sir? You please concentrate. But this, whatever the DC offset is there, I told already. From phase to phase it changes. A phase to B phase, B phase to C phase, C phase to. Then like that, the phase to phase it is changes. That's why I given this waveform separately for by considering the DC offset effect. Because of DC offset effect, there is a which effect is there, sir? Because of DC offset effect, there is an unsymmetrical response. Understood, sir? Okay, this is for each phase. This is for phase A, phase B, and phase C. It's a three-phase short circuit fault currents. Now, this is the short circuit current decrement curve, sir. This I am drawing this decrement curve. By seeing this one directly also we can calculate the what is I double dash. This is IF double dash, this is IF dash, and this is IF. This delta I double dash gives the difference between the this delta I double dash gives the difference between the that is subtransition fault current and the transition fault current, sir. What the delta I dash gives, sir? This delta I dash gives the difference between the that is the fault, that is difference between the steady state current and the transition fault current. Steady state current and transition fault current, sir. Now from this one, after this we can get the steady state, sir. After this we can get the steady state condition. After the transition period, we are getting the steady state period. Now after this we are getting the steady state. Now it is taken as a steady state current, sir. It is taken as a steady state current. Now you tell me, sir, if you calculate what is OC, sir, let this point is OC. What is OC, sir? This IF double dash. I am taking this IF double dash. This IF double dash equal to OC by root 2, sir. OC by root 2. Okay, this is IF double dash equal to this OC by root. This total is IF double dash. IF double dash. Then it's a large magnet. This what is IF? How to get this? I am taking this IF double dash is because it's a maximum value, sir. Then IF double dash you want means you can write OC by root 2, sir. You please concentrate. OC by root 2. This is equal to which one, sir? EZ by EZ double dash by, sir, or EZ by XD double dash. EZ by XD double dash. EZ by XD double dash. Yes, sir. Now what is IF dash, sir? IF dash. This, sir. From this one you directly calculate. This IF dash equal to this one, sir. OB by root 2, sir. How you can write this one, sir? EZ by XD dash. EZ by XD dash. Similarly, how to write IF, sir? IF is, this is the steady state period, sir. This is the steady state period. The steady state period is, the currents are less, sir. Under steady state condition, this is OA by root 2, sir. OA by root 2. That means, OA by root 2 means how you can write this one, sir? EZ by XD. EZ by XD. These are the not maximum values, sir. These are the RMS values. Directly I am substituting RMS value of the voltage. This EZ is the RMS value of the excitation values, not the maximum values. But if you take directly from this one, this gives the maximum value of current. That's why I am substituting by root 2. I am doing by root 2, sir. This is IF double dash. This total gives the IF double dash. This gives the I dash. This gives the IF. Sir, it is subtransient period. This is the transient period. After this, we can get this. This constant indicates this is transient. This constant value of current indicates this is the current under which conditions are steady state condition. Okay, like this also directly by using this incremental curve. By using this decrement curve of alternator, directly you can calculate the IF double dash, IF dash, and the IF, sir. Yes, students, you please concentrate. Yes, sir. Here here I am giving one note, sir. Here I am giving one note. By calculating subtransient time, that is subtransient time period, and transient time periods. Subtransient time period and transient time periods. Transient time periods. We can calculate instantaneous value of current. We can calculate instantaneous value of current, sir. Calculate instantaneous value of fault current. Instantaneous value of symmetrical fault currents. Symmetrical fault current. Then how you can calculate, sir? This I am giving generalized equation. If you want the instantaneous fault current IF equal to, then you can define like this, sir. I double dash minus I dash into e power minus t by t double dash plus this t double dash is the subtransient time period, sir. I dash minus I, that is the difference between the transient current and the steady state current, into e power minus t by t double dash plus I, sir. Okay, like this we can calculate. Then if you want to define this one, this is the instantaneous value of total fault currents. What is I double dash, sir? This is EZ by XD double dash minus what is I dash, sir? EZ by XD dash. EZ by XD dash into e power minus t by t double dash plus what is I dash, sir? EZ by XD dash minus what is I, sir? This is EZ by XD into e power, it's not t double dash, sir, it's a t dash. Please concentrate. It's a t. This is a transient period. It's not subtransient period, it's transient period. Then e power minus t by t dash plus I. What is I, sir? EZ by XD. EZ by XD. Okay, like this we can calculate total fault current by calculating the subtransient period and the transient period. This also you remember. Yes, students, you please concentrate. Yes, sir. One more observation, one more note also I want to use, sir. If you draw the characteristics between, reactance and time, XD, that is reactances and time. Let assume that we are getting the during subtraction period, this is the reactance we are getting XD double dash. Then during transition period, this is increases, that reactance is XD dash. Then again for during steady state period, we are getting this one. Now if you join this one, we can get the curve like this, sir. We can get the curve like this. Okay, this is the curve we can get for direct access reactance and we can get the curve like this. Yeah, this is, we can get this curves. We can get this curve. Yeah, this is the variation of XD with respect to time. Variation of the XD with respect to time. This is XD double dash and this is XD double dash and then that one is XD, sir. This is XD. Okay, this XD remains constant. This XD remains constant. Yeah, this is which one, sir? This period is subtransition period. This period is transition period. And this is which ones are steady state period. Steady state period. Yeah, this observation also you remember. Then slowly the reactance is increased. But what are the fault currents? The fault current is exactly opposite we can get. Okay, this is the reactance with respect to time I am drawing. With respect to time I am drawing the characteristics. You please pass. That means we can get the curve like this. This reactance remains constant. That reactance remains constant. What is this reactance, sir? XD. This XD is remains constant. Clear, sir? Okay, this you concentrate. Okay, this is about what is the observations from. What is the observations from three-phase short circuit analysis of the alternator. Three-phase short circuit analysis of alternator. Sir, here one more note. What is the calculation of momentary current for based on the fault? How we can calculate the momentary current based on the faults? Based on the fault. How we can calculate, sir? Generally for one cycle or 1 to 2 cycles, momentary is you can calculate like this, sir. How we can calculate the momentary current based on the faults? Yeah, this I am giving this one how to calculate. Please concentrate. Yes, sir. For one cycle, for up to one cycle, if you take this one cycle, it's a cycle. AC component, that is AC component. That is AC component. AC component. Then you take a DC component effect. DC component effect. DC component effect. Yes, sir. Instantaneous or momentary current. It is a momentary current. Momentary current. How you can calculate momentary current? Here AC component means you take IF double dash with respect to IF double dash. DC component effects. If there is one cycle, for one cycle, you can take for one cycle, this is IF double dash. You take this is IF double dash. For one cycle, you can take this is IF double dash, sir. Then if it is up to for one cycle, we can calculate this DC component effect is taken as a 1.6, sir. Then how we can define momentary current? The momentary current Im equal to 1.6 times of IF double dash. 1.6 times of IF double dash. This is multiplication factor we can use. But if it is a 2 cycles, sir, if it is actually we are taken subtransition period is a 2 cycles. If it is extend for more time, then how we can calculate? Then it is 2 to 3 cycles. For 2 to 3 cycles, this is the IF double dash. For IF double dash, we can use 1 point. DC effect, we can take 1 point. This is for asymmetrical, sir. Calculation of the momentary current of the faults for its asymmetrical waveform. For asymmetrical waveform. I am talking about asymmetrical waveform. It's asymmetrical. If it is a 2 to 3 cycles, if you take, you multiply with 1.4, sir. This 1.4 into IF. If it is a 4 to 5 cycles, then the momentary, let the AC component of current is IF double dash, DC effect, then you can take the DC effect is. You take the DC effect, how much you can consider, sir? 1.2 you can consider. Then what the momentary current you take? 1.2 times of IF. 1.2 times IF. Yes, sir. This is 4 to 5 cycles, 1.2 times. Then if it is up to 8 cycles or more, sir. 8 cycle or more. 8 cycles or more cycles. Then you take this IF double dash is the momentary current. Then you take the DC effect is 1.0, sir. Then you get IM equal to this IM equal to, then you can get 1 into IF double dash. Okay, like this you can calculate. This is for asymmetrical waveforms. For asymmetrical current waveform, how you can calculate the momentary current? For the asymmetrical current waveform, there is any fault is occur, if it is a combination of both AC plus DC, then for asymmetrical waveforms. This point you remember. Okay, this is about calculation of momentary current based on the number of cycles. Based on if it is exists for only 2 to 3 cycles, then you can calculate 1.4. It is exists for only one cycle. That is high fault current is exists for only one cycle. Then you can take 1.6 times of IF double dash. Yes, sir. You take this is the calculations. Okay, this is the AC component of current. Yes, AC. By calculating AC instead of this one, you take this is the correct, sir. Okay, no problem. This is the correct one. Yes, sir. Next, one more point to remember. What is the effects of open circuit and short circuits on a fault? What are the effects of open circuits and short circuits on a fault? Okay, that you concentrate, sir. That means, sir, if you consider the open circuit and short circuits, what is the effects? Okay, this also you write as a notes. If you take the fault, and what is the voltage under fault condition? Sir, what is the current under fault condition? What is the current under fault condition? What is the power factor? What is the frequency? If you take this, if it is a short circuit fault, sir. If it is a short circuit fault, then under short circuit fault, what is the voltage, sir? Almost zero. It's almost zero. Under short circuit condition, voltage is almost zero. But what are the currents, sir? You can get very high currents. Current must increases. But what are the power factors, sir? It is zero lagging or reduced depending on the pi. It is a zero ZPF. I told already this one ZPF or reduced based on angle. It reduces based on the angle. What are the frequencies, sir? Frequencies increases under short circuit condition. Then what about for open circuit faults, sir? For open circuit faults, if you take the open circuit faults, what is the voltage, sir? What is the voltage? This voltage is open circuit fault voltage is increases. Under open circuit condition, it's not zero, sir. Increases. But what is the current, sir? It's a zero. Current is almost zero only. It's almost zero. But what the power factor, sir? Under open circuit condition, the power factor is increases. Power factor, because system voltage is increasing, the power factor is increases. But what the frequency? Here also increases. Frequency is increases. Here also frequency is increases. Okay, that you point to remember. Okay, this is the observation effects of open circuit and short circuit faults. Because of short circuit faults, voltage is almost zero. Because of short circuit, we can get the current is increases, power factor is reduces, but frequency is increases. But under open circuit faults, it is also increases. But open circuit means current is zero. Then what the power factor is increases because system voltage is increases. Then what is the frequency? Frequency is also increases. Okay, these are the observation effects of open circuit and short circuit faults. Okay, this about in detail what exactly short circuit fault and alternators. In the last session in detail that I given what the short circuit fault on a transmission line, what the short circuit fault on a alternator. This today's session I complete. Sir, please concentrate. What are the formulas I given? That formulas you concentrate. Very important concept that I discussed today. That is more important for GATE, ESE and PSU's point of. Yes, students, follow me on Unacademy using this Unacademy user link for more updates about my videos. Sir, this is our Unacademy GATE Telugu Telegram channel, sir. You subscribe this channel, you register this channel. Every day, whatever the concepts we are explaining, all those concepts uploaded as a PDF material that is more useful for you. Sir, these are India's #1 study channel, sir. Creatics GATE, Electrical ECE and Instrumentation, Unacademy GATE, Mechanical Engineering, Unacademy GATE Civil Engineering, Unacademy GATE Telugu, Unacademy SSC JE, Unacademy Computer Science, Unacademy GATE Questions, Electrical Junction, Engineering Padashala, GS Terminal, RRB and SSC. Sir, all these are India's #1 study channels. Please subscribe all these channels for more updates on different concepts and different subjects. Okay, students, thank you. We will continue tomorrow, that is next Monday only. Sunday you concentrate on the whatever the crash course subjects are there. That crash course subject you concentrate. Next session we will continue with the new concept on the fault analysis. On the fault analysis only. Next session we have one theory concept with respect to fault analysis. After completing that theory concept, then we will start the solving of the problems of fault analysis. After solving the practice question, then we will see the GATE, ESE and the PSU questions. Okay, students, thank you.